Hello friends, welcome to YouTube channel Electronics. In this video, we will learn how to perform addition and subtraction of the signed binary numbers using 2's complement method. Let's start with addition of two positive numbers. Here we will represent these two positive numbers in the 5-bit binary form. This plus 9 can be represented as 01001 and this plus 5 can be represented as 00101. If we observe over here, the MSB or sign bits of both numbers are 0, which indicates that they are positive binary numbers. Here the addition is very similar to the normal binary addition. We will use column by column method. These are the basic rules for binary addition. By using these rules, we must start adding from the LSB. So 1 plus 1 equals to 0 with carry 1. In next column, we have 1 plus 0 plus 0. That equals to 1. Next 0 plus 1. That equals to 1. Next 1 plus 0. That equals to 1. In last column MSB bits 0 plus 0. That equals to 0. So after the addition, the answer is 01110. Here the MSB is equals to 0. That means the answer is a positive binary number. This is nothing but decimal equivalent of plus 14. In this way, we can perform the addition of two positive binary numbers. Here we know that in 2's complement form, by using n bits, the range of binary numbers that can be represented are from minus 2 to the power of n minus 1 to plus 2 to the power of n minus 1 minus 1. So for the 5 bits, it is in the range from minus 2 to the power of 5 minus 1 to plus 2 to the power of 5 minus 1 minus 1. That equals to decimal equivalent of minus 16 to plus 15. So after the addition, if the result is out of this range, then we will get invalid result, or it can be called as overflow condition. Let's discuss this overflow condition with an example. Here if we want to add these two positive numbers plus 9 and plus 8 in 5-bit format, first represent these two numbers in 5-bit binary format. Plus 9 can be represented as 01001 and plus 8 can be represented as 01000. Here the MSB or sign bits are 0, which shows positive binary numbers. Here we must follow the normal binary addition process and we will follow column by column method and must start from LSB. So first 1 plus 0, that equals to 1. Next 0 plus 0, that equals to 0. Next also 0 plus 0, that equals to 0. Then 1 plus 1, that equals to 0 with a carry of 1 to the next column. In the last MSB column, we have 1 plus 0 plus 0, that equals to 1. Here this 9 plus 8 equals to 7. But as we know that in 2's complement form, using 5 bits, the range of numbers which can be represented are between minus 16 to plus 15. So this plus 17 is out of range of 5-bit representation. And here we can also notice that the MSB bit of the answer is 1, which indicates that the negative signed binary number. Here we are adding two positive numbers. So the answer must also be a positive number with MSB as 0. So by looking at the answer, we can say that the answer is incorrect. This means whenever the answer is beyond the range of 2's complement representation, then we will get an invalid result and can be said as overflow condition. Now let's see another example. Addition of a positive and a negative number. Plus 14 plus minus 7. Here the positive number is greater than the negative number. First we will represent 14 in a 5-bit form, that is 01110. Here the MSB is 0, which shows positive representation. Now this minus 7 is nothing but 2's complement of plus 7. So plus 7 in 5-bit form is equals to 00111. In previous video, I have explained how to find 2's complement of a binary number. Here to find 2's complement of plus 7, first of all, we convert convert plus 7 into 1's complement form. That is, just flip all 1's with zeros and zeros with 1's. After that, just add 1 to it. Here 0 plus 1 equals to 1. Remaining all bits comes as it is. Then the result is the 2's complement representation of minus 7. Here MSB is 1, which shows negative number. Hence the minus 7 in 5-bit 2's complement form is nothing but 11001. Now we will add both these binary numbers plus 14 and minus 7. To add both these numbers, we must follow column by column method and we'll start adding from LSB. 0 plus 1 equals to 1. 1 plus 0 equals to 1. Next 1 plus 0, that equals to 1. Here 1 plus 1, that equals to 0 with a carry of 1 to the next column. Next also 1 plus 1, that equals to 0 with a carry of 1. Here we must ignore this carry. Now the result must be equals to plus 7. That's it. 00111 in binary form. Here we can see that MSB bit is 0, which indicates this binary number is positive. This is how we will do the addition. Now let's quickly move into the next example. Addition of negative and positive numbers. Minus 13 plus 6. Unlike the previous example, here the negative number is greater than the positive number. First of all, we can easily represent this plus 6 in 5-bit form. That is 00110. Here MSB is 0, which indicates positive number. Next we must find equivalent representation of minus 13. That is 2's complement of plus 13. So in 5-bit plus 13 can be represented as 01101. To find 2's complement, first we will convert it into 1's complement form. That can be done by inverting 1's with zeros and zeros with 1's. 10010 is the 1's complement representation of plus 13. Next we will add 1 to this number. 0 plus 1 equals to 1. Rest of all numbers are brought as it is. This result 10011 is the minus 13 in 2's complement form. Here we can see that MSB is 1, which indicates negative number. So in this example, plus 6 in 5-bit form is 00110 and minus 13 in 2's complement 5-bit form is 10011. Now we will add both these numbers, minus 13 and plus 6. Here we must follow column by column method and must start from LSB. 1 plus 0 equals to 1. Next 1 plus 1, that equals to 0 with a carry of 1 to the next column. Again 1 plus 1, that equals to 0 with a carry of 1 to the next column. Next 1 plus 0, that equals to 1. Finally 1 plus 0, that equals to 1. So the result is 11001. Here MSB is 1, which indicates that the result is negative. This result is nothing but minus 7 in 2's complement form. Now let's convert this result to get corresponding positive number. To find 2's complement of this number, we will follow an easy way. Here starting from LSB, just find first one and copy all bits as it is until the first one. And then after, just invert all zeros by ones and ones by zeros. So the resultant 2's complement of the number is 00111 and it is decimal equivalent of plus 7. Therefore, we can say that the above number is minus 7. Thus it is. Here the addition of minus 13 and plus 6 gave the result of minus 7. So our solution is correct. Now we will solve one more example. Here in this example, we will add two negative numbers, minus 7 and minus 5 using 2's complement form. First of all, we will represent minus 7 and minus 5 in 2's complement form. Minus 7 is nothing but 2's complement of plus 7. So in 5-bit, plus 7 can be represented as 00111. Once again, to find 2's complement representation, we must convert this number into 1's complement. That can be done by inverting 1's with zeros and zeros with 1's. So 11000 is 1's complement representation of plus 7. Now we will add 1 to this 1's complement number to get 2's complement representation. Here 0 plus 1 equals to 1 and rest of the numbers are brought as it is. The resultant number 11001 is the minus 7 in 2's complement form. Here MSB is 1, which shows negative number representation. Likewise, minus 5 is the 2's complement of plus 5. So in 5-bit, plus 5 can be represented as 00101. Now we will convert into 1's complement by inverting all bits, 1's with zeros and zeros with 1's. Next we will add 1 to this number. 0 plus 1 equals to 1 and rest of all the numbers are brought as it is. The resultant number 11011 is the minus 5 in 2's complement form. Here also MSB is 1, which means negative number representation. Hence minus 7 in 2's complement 5-bit representation is 11001 and minus 5 in 2's complement 5-bit representation is 11011. Now we will add both these binary numbers minus 7 and minus 5. Binary addition must be done by column method starting from LSB. So here LSB column is 1 plus 1, that equals to 0 with a carry of 1. In next column it is 1 plus 1, that equals to 0 with carry of 1. In next column it is 1 plus 0, that equals to 1. Now in next column it is again 1 plus 1, that equals to 0 with carry of 1. In final or MSB column it is addition of 3 1's, that equals to 1 with carry of 1. Here we must ignore this carry. So the result is 10100. That must be equals to minus 12. Here we can confirm negative number by looking at the MSB bit. It is 1. So negative number representation. Here this result is in 2's complement form. So let's again convert this 2's complement form to get corresponding positive number to check our result. To convert this number, starting from LSB, just identify the first one and copy all the bits as it is until this first one. Then after invert all bits. So the resultant positive number is 01100 and the decimal equivalent of this binary number is plus 12. Therefore, the above binary number is minus 12. Hence our answer is correct. If we observe over here, after the addition of these two negative numbers, the result is within the 5-bit 2's complements range of minus 16 to plus 15. If the result goes beyond this range, then overflow condition will occur and the result becomes invalid. So let's discuss this overflow condition with an example. Here we will add these two negative numbers, minus 8 and minus 9. Our result must be minus 17. As we know that using AND bits, we can represent binary numbers in 2's complement form from minus 2 to the power of n minus 1 to plus 2 to the power of n minus 1 minus 1. So if you use 5-bit representation, we can represent binary numbers in 2's complement form from minus 2 to the power of 5 minus 1 to plus 2 to the power of 5 minus 1 minus 1. That is nothing but minus 16 to plus 15. But here minus 8 minus 9 equals to minus 17. This result is beyond 5 bits 2's complement range. This means if we use 5-bit form in this addition, we will get overflow condition or invalid result. Here we will go with 5-bit binary addition to observe how the overflow condition or invalid result occurs. First of all, we will represent minus 8 and minus 9 in 2's complement form. Minus 8 is nothing but 2's complement of plus 8. So in 5-bit, it can be represented as 01000. Now we will convert this number into 2's complement form. So starting from LSB, just identify the first one and copy all the bits until this first one. Then after invert the remaining bits. So this 11000 is the 2's complement representation of minus 8. Let's do the same thing with minus 9. This minus 9 is nothing but 2's complement of plus 9. In 5-bit form, plus 9 is represented as 0, 1, 0, 0, 1. Now to convert this number into 2's complement form, starting from LSB, identify the first one and copy all the bits up to this bit. Then after, invert all bits zeros with ones and ones with zeros. The resultant binary number 10111 is the 2's complement representation of minus 9. Now we will do binary addition of both these numbers 11000 and 10111. To do binary addition, we must follow column by column method and must start adding from LSB. So here 0 plus 1 equals to 1. Next 0 plus 1, that equals to 1. Next also 0 plus 1, that equals to 1. Next 1 plus 0, that equals to 1. And finally 1 plus 1, that equals to 0 with a carry of 1 to the next column. Here we must neglect this carry. Here after adding these two negative numbers minus 8 and minus 9, our result must be minus 17. But if we observe over here, MSB bit is 0. It means the result is a positive number. Hence by checking the MSB bit, we found that our addition is incorrect. This is happened because in 5-bit 2's complement representation, the range is minus 16 to plus 15 and this minus 17 is out of range. So we got invalid result. Hence we must be careful of range when doing 2's complement arithmetic. Otherwise we will get overflow or invalid result. Alright, now let's discuss how to do subtraction using the 2's complement form. The 2's complement subtraction is very similar to the addition. Let's say if you want to subtract these two numbers 8 minus 5. We can represent this 8 minus 5 as 8 plus minus 5. So it is equals to 8 plus 2's complement of minus 5. Now this 8 can be represented as 0, 1, 0, 0, 0 in 5-bit form. And this minus 5 is nothing but 2's complement of plus 5. This plus 5 can be represented as 0, 0, 1, 0, 1. Here we will convert this binary number into 2's complement form. To do this, starting from LSB, identify the first one and copy all the bits as it is up to this first one. Then after, invert all bits zeros with ones and ones with zeros. The resultant number 11011 is the 2's complement representation of minus 5. Now we can perform the subtraction. Here we need to add these two binary numbers plus 8. 0, 1, 0, 0, 0 and minus 5 1, 1, 0, 1, 1. So let's perform the addition between these two binary numbers. Here we must follow the column by column method and must start from LSB. So this 0 plus 1 equals to 1. Next 0 plus 1, that equals to 1. Next 0 plus 0, that equals to 0. In next column it is 1 plus 1, that equals to 0 with a carry of 1 to the next column. Finally, MSB column. It is also 1 plus 1, that equals to 0 with a carry of 1 to the next column. We must ignore this final carry. We must get the answer of plus 3. That's it is. This 00011 is the binary representation of plus 3. If we observe over here, MSB bit is 0. This shows the positive binary number. Hence, by using 2's complement, we can perform subtraction just like addition. Now let's solve one more example. Here we will subtract 9 minus minus 4, which is just equivalent of 9 plus 4. It is because 9 minus minus 4 is equivalent of 9 plus 2's complement of minus 4. And as we know that 2's complement of negative number is positive. So here 2's complement of minus 4 is equals to plus 4. So to perform subtraction, we need to add plus 9 with plus 4. So here plus 9 in 5-bit form is 01001 and plus 4 in 5-bit form is 00100. Now we will add these two binary numbers. We must follow column by column method and must start adding from LSB. So here 0 plus 1 equals to 1. 0 plus 0 equals to 0. 0 plus 1 equals to 1. 1 plus 0 equals to 1. And 0 plus 0 equals to 0. That's it. 9 plus 4 equals to 13. And this 0 1 1 0 1 is the decimal equivalent of plus 13. In this way we can perform subtraction using 2's complement method. Now let's solve the final example. Here we will perform subtraction between these two binary numbers 11001 minus 01100. By looking at the MSBs of both numbers, we can recognize that first number is a negative number and second one is the positive number. So let's convert this first number in 2's complement form so that we can know the decimal equivalent of this number. To convert this number, just start from LSB and identify the first one and copy all the bits up to first one and invert remaining bit zeros with ones and ones with zeros. Now this 00111 is the decimal equivalent of plus 7. Hence the decimal equivalent of the above binary number is minus 7. Now the second binary number 01100 is the decimal equivalent of plus 12. So if you perform subtraction between minus 7 and plus 12, we must get minus 19 as an answer. Let's perform the binary subtraction. First of all, we must change this plus 12 in 2's complement to get minus 12 value so that we can add both these numbers. To convert this number in 2's complement form, start from LSB and identify the first one. Copy all the bits up to this first one. Then invert the remaining bits. So this 10100 is the 2's complement representation of minus 12. Now in this example, we will erase this plus 12 value and just write the minus 12 value of 10100. And now here this subtraction becomes addition of two negative numbers. So just add both these negative numbers minus 7 and minus 12. Let's do the column by column addition starting from LSB. 1 plus 0 equals to 1. 0 plus 0 equals to 0. 0 plus 1 equals to 1. 1 plus 0 equals to 1. And 1 plus 1 equals to 0 with carry of 1 to the next column. And here we must ignore this carry. Here we must get minus 19 as answer. But if you observe, the MSB bit of the result is 0. Hence this binary number is positive. So our result is not correct. Why we got this incorrect result? The reason is very simple. By using 5-bit, we can represent binary numbers from minus 16 to plus 15. Here the result minus 19 is out of 5 bits range. Therefore we got incorrect or overflow condition. But for the same numbers, if you do the subtraction in 6-bit form, we will get correct result. It is because in 2's complement 6 bits, we can represent the numbers between minus 32 to plus 31. So the result will comes in this range. So we will represent both the numbers in 6-bit 2's complement form. To represent this 5-bit 11001 in 6-bit form, we need to copy the MSB bit as an additional bit. So 111001 is the 6-bit representation of minus 7. For second number 01100, we will do the same thing. We must copy MSB bit 0 as an additional bit. Hence 001100 is the 6-bit representation of plus 12. Now we will find 2's complement of plus 12 to get the value of minus 12. To convert this number, we must start from LSB and will identify the first one. We will copy all bits as it is up to this first one and will invert all bits after that. So 110100 is the 6-bit representation of minus 12. Now we will erase this plus 12 value and will write minus 12 value of 110100 in this example. Hence this subtraction becomes addition. So now we can add both these 6-bit binary numbers of minus 7 and minus 12. Starting from LSB, 1 plus 0 equals to 1. 0 plus 0 equals to 0. 0 plus 1 equals to 1. 1 plus 0 equals to 1. 1 plus 1 equals to 0 with carry of 1 to the next column. In final column we must add 3 ones, that equals to 1 with carry of 1. Here we must ignore this carry. So our result is 101101. If we observe over here, MSB bit is 1, which shows this result is negative number. Now we will convert this negative result into 2's complement form to get decimal equivalent of the result. So starting from LSB, we will identify the first one and will copy all the bits as it is up to this bit, and will invert remaining bits, zeros with ones and ones with zeros. Here this 010011 is nothing but decimal equivalent of plus 19. That means our result corresponds to minus 19 in 2's complement form. Here we can observe that in 6-bit form we are getting correct result. So while doing addition or subtraction in 2's complement form, we must be very careful about the range. In a CPU, ALU performs all arithmetic operations and it typically uses 2's complement method due to its simplicity and efficiency. A 32-bit CPU is less capable than a 64-bit CPU because a 64-bit CPU can handle more data at once. Generally, 32-bit CPUs have 32-bit ALUs and 64-bit CPUs have 64-bit ALUs. So this allows a 64-bit CPU to efficiently process larger values than a 32-bit CPU. That's all about 2's complement arithmetic. If you have learned from this video, please do mention them in the comment section below. Thanks for watching. If you like this video, please click the like button. Help others to learn by sharing this video. Please subscribe and turn on notifications for more such videos. Have a nice day.